At 5, exponential 32 is below linear 50. At 6, exponential 64 is above linear 60, so the crossing is between 5 and 6.
If you want to see how quantities change over time, you can watch the math happen right here in the natural environment of Hazel Grove Hollow. We are going to track the journey of a single red squirrel as it moves along two very different mathematical paths, leaving caches of acorns at each step. The first path follows a linear model, written as L of x equals 10x. In this model, a constant amount is simply added at every step. 10 acorns for step 1, 20 for step 2, and so on. The second path follows an exponential model, written as E of x equals 2 to the power of x. Here, the total doesn't just add up, it multiplies by a constant factor at each step. Let's see what these paths look like when the squirrel reaches time step x equals 4. This table compares the outputs for both models. At step 4, the exponential path yields 16 acorns. The linear path, however, sits at 40 acorns. Early on, the linear model has a commanding lead. Judging the trajectory of growth solely by this early short-term data creates an illusion. It makes a simple additive model look far superior to a multiplicative one. Time passes. We move further down the hollow, following our squirrel's path, to test the models at a later stage. At step x equals 5, the exponential model reaches 32. The linear model sits at 50. The multiplication is catching up, but it is still lagging behind. Step 6 is where a critical threshold is crossed between the two paths. This graph plots the exact values. At x equals 6, the exponential model hits 64, surpassing the linear model 60. Jumping to step 8, it's a blowout. The exponential hits 256, leaving the linear behind at 80. The mechanism causing this divergence is simple. Multiplying a number that is already growing accelerates the output much faster than repeatedly adding a fixed number. The internal engine of exponential multiplication guarantees it will eventually crush linear addition, regardless of any initial head start.
At 2 and 4, the values tie. At 3, quadratic 9 is greater than exponential 8. At 5, exponential 32 is greater than quadratic 25. Now compare q of x equals x squared with e of x equals 2 to the x. At x equals 2, both functions equal 4. At x equals 3, q of 3 equals 9 while e of 3 equals 8. So the quadratic is ahead by only 1. At x equals 4, both functions equal 16. At x equals 5, e of 5 equals 32, while q of 5 equals 25. At x equals 6, 64 is greater than 36. These displayed inputs show two ties, one brief quadratic lead, and then the exponential lead from x equals 5 onward. The data do not show a runaway quadratic lead. Eventually is a long-run claim, not a claim that the exponential is larger at every input.
To resolve the question of predicting growth, we can look at a final analytical proof laid out right in the environment.
The student's two checks are correct. 3 times 2 equals 6, greater than 4, and 3 times 3 equals 9, greater than 8. One more check reverses the comparison. 2 to the 4th equals 16, greater than 3 times 4, which equals 12. Early values do not decide long-run behavior. The general claim requires e of x equals a times b to the x, with a greater than 0 and b greater than 1. The overflowing acorn caches illustrate the long-run pattern. They do not prove it. The table and graph supply the evidence for these models. Which displayed values show the exponential first moving ahead, and which equation explains why the gap keeps growing?
As Hazel rests at the end of the hollow, the timeline journey is complete.
Eventually is not every input. For e of x equals a times b to the x, with a positive and b greater than 1, exponential growth eventually exceeds polynomial growth. Tables show where the comparison changes. Eventually is not every input. For e of x equals a times b to the x, a must be positive and b must be greater than 1.